Many people believe that Earth's distance from the sun causes the seasons. This is a common misconception. It's easy to see why this idea persists. After all, when it's summer, the sun feels closer and hotter. In winter, the sun feels distant and weak. However, the truth is far more interesting. Earth's orbit around the sun is not a perfect circle. It's an ellipse, a slightly elongated shape. This means that Earth is sometimes closer to the sun and sometimes farther away. You might be surprised to learn that Earth is actually closest to the sun in January, during the northern hemisphere's winter. So, if distance isn't the reason for the seasons, what is? The answer lies in a fascinating phenomenon: Earth's axial tilt. Earth's journey around the sun is a captivating dance, a celestial waltz that takes approximately 365 days to complete. This journey is not a perfect circle, but an ellipse, a slightly elongated shape resembling an oval. As Earth travels along this elliptical path, its distance from the sun changes throughout the year. At its closest point, known as perihelion, Earth is approximately 91.4 million miles from the sun. This event usually occurs in early January. Conversely, at its farthest point, called aphelion, Earth is about 94.5 million miles from the sun, typically happening in early July. This variation in distance might seem significant, but it has a surprisingly small impact on Earth's temperature and seasons. The real key to understanding the changing seasons lies in another aspect of Earth's movement: its axial tilt. Earth spins on its axis, an imaginary line passing through the north and south poles. This axis is not perfectly straight up and down, but is tilted at an angle of approximately 23.5 degrees. This tilt, known as Earth's axial tilt, is the primary reason we experience seasons. Because of the tilt, different parts of Earth receive varying amounts of direct sunlight throughout the year. During summer in a hemisphere, that hemisphere is tilted towards the sun. This means the sun's rays hit the Earth at a steeper angle, delivering more concentrated energy and leading to warmer temperatures. Conversely, during winter, the hemisphere is tilted away from the sun. The sun's rays strike at a shallower angle, spreading the energy over a larger area and resulting in colder temperatures. The sun, our very own star, is a dynamic and fascinating celestial object, constantly in motion and full of surprises. Beyond providing us with light and heat, the sun exhibits various phenomena, one of the most intriguing being sunspots, which have captivated scientists for centuries. These dark, cooler regions on the sun's surface may seem insignificant from our vantage point, but they have a profound impact on Earth and its technological systems, influencing everything from satellite operations to power grids. Sunspots appear darker because they are cooler than their surroundings, but don't let that fool you. They are still incredibly hot, with temperatures reaching around 6,500 degrees Fahrenheit, which is hotter than any temperature found on Earth. These spots are caused by intense magnetic activity within the sun, which can be both fascinating and complex to understand. The sun's magnetic field lines can become twisted and tangled, creating areas of concentrated magnetic flux, which are the birthplaces of sunspots. These concentrated magnetic fields inhibit the flow of heat from the sun's interior, causing the surface temperature to drop and resulting in the formation of sunspots, which can last for days, weeks, or even months. The number of sunspots visible on the sun's surface varies over an 11-year cycle, known as the solar cycle, which affects solar radiation and space weather, impacting our planet in numerous ways. Section 5. Sunspots and radio waves, a historical perspective. Sunspots have intrigued astronomers and scientists for centuries, but their impact extends far beyond the realm of astronomy. In the early days of radio communication, people discovered a fascinating connection between sunspot activity and the propagation of radio waves. During periods of high sunspot activity, radio signals could travel surprisingly long distances, sometimes even across continents. This phenomenon arises from the sun's influence on Earth's ionosphere, a region of the upper atmosphere ionized by solar radiation. Sunspots are often associated with solar flares and coronal mass ejections, which release bursts of energy and charged particles into space. These particles interact with the ionosphere, increasing its ionization and altering its ability to reflect and refract radio waves. This enhanced ionization creates a sort of radio mirror in the sky, allowing radio waves to bounce off the ionosphere and travel much farther than they normally would. Section 6. The dark side of the sun, solar storms. While increased sunspot activity can enhance radio communications, it also has a darker side: solar storms. These storms are caused by sudden releases of energy from the sun, often associated with sunspots and solar flares. During a solar storm, the sun unleashes a barrage of charged particles and radiation, known as a coronal mass ejection, or CME, into space at incredible speeds. These CMEs can wreak havoc on Earth's technological infrastructure. When a CME collides with Earth's magnetic field, it can trigger geomagnetic storms, disrupting radio communications, GPS navigation systems, and even power grids. One of the most famous examples of a solar storm's impact occurred in 1859, known as the Carrington event. This massive solar storm caused widespread telegraph system failures, sparking fires and delivering electric shocks to operators. Section 7. When solar winds collide, impacts on Earth. Imagine a constant stream of charged particles, a solar wind emanating from the sun and flowing through space. This solar wind is composed of electrons, protons, and other particles that travel at incredible speeds, reaching up to 900 kilometers per second. When this solar wind collides with Earth, our planet's magnetic field acts as a shield, deflecting most of these particles and protecting us from their harmful effects. This magnetic field, known as the magnetosphere, is crucial for maintaining life on Earth. However, during solar storms, the intensity of the solar wind increases dramatically, putting our technological systems at risk. These storms are often caused by solar flares or coronal mass ejections from the sun. One of the most vulnerable systems is our reliance on satellites. These satellites are essential for communication, navigation, and even scientific research. Solar storms can damage satellite electronics, disrupt their communication links, and even drag them out of orbit. This can lead to significant disruptions in the services they provide. These disruptions can impact a wide range of services, from GPS navigation and weather forecasting to television broadcasting and internet connectivity. The ripple effects can be felt across various sectors of society. Furthermore, solar storms can induce electric currents in power grids, potentially overloading transformers and causing widespread blackouts. These induced currents can travel through power lines, leading to severe damage. The 1989 Quebec blackout, which left millions of people without power, serves as a stark reminder of the potential consequences of solar storms on our power infrastructure. This event highlighted the vulnerability of our modern technological systems to space weather. Section 8. Connecting the dots: seasons and solar weather. At first glance, the changing seasons on Earth and the dynamic behavior of the sun might seem unrelated. However, both phenomena are intertwined, showcasing the profound influence of our star on our planet. Earth's axial tilt, responsible for the seasons, determines the amount of direct sunlight different parts of Earth receive throughout the year. Simultaneously, the sun's activity, including sunspots and solar storms, affects us in ways we often overlook. From enhancing radio communications to disrupting our technological systems, solar weather has a tangible impact on our daily lives. Understanding the connection between Earth's seasons and solar weather allows us to appreciate the intricate balance that governs our planet and its relationship with the sun. Section 9. The sun's powerful influence, a call to appreciation. As we delve into the intricacies of Earth's seasons and the sun's dynamic behavior, we gain a deeper appreciation for the powerful influence of our star. The sun's energy is the driving force behind the changing seasons, dictating the rhythm of life on our planet. The sun is not merely a source of light and heat. It is a celestial engine that drives our weather patterns, shapes our planet's environment, and even affects our technological systems. Solar energy powers our homes and industries, while solar storms can disrupt communications and navigation. From the beauty of a summer sunrise to the awe-inspiring display of the aurora borealis, the sun's presence is constantly felt on Earth. Its light nurtures our crops, warms our oceans, and provides the energy necessary for life itself. By understanding the science behind these phenomena, we can marvel at the intricate workings of our solar system and the profound connection between Earth and its star. The sun's gravitational pull keeps our planet in orbit, maintaining the delicate balance necessary for life. Let us take a moment to appreciate the sun's energy and power, recognizing its role in shaping the world around us. Every sunset and sunrise is a reminder of the sun's unwavering presence and its vital importance to our existence. As we continue to explore the cosmos, we will undoubtedly uncover even more fascinating connections between our star and our planet, deepening our understanding of the universe we inhabit. The sun, our constant companion, holds many secrets yet to be discovered.